the popping force, right? So how do you find we look at the solutions, right? So how does tree popping force being determined? Sorry? Okay, it's not only for the P1, P2. If you look at the structure, right? So maybe I just address the first question, how do you determine the popping force, right? So what is actually, I'm just going to use tutorial 1, session 3B to make an illustration. Right, so where is actually this popping force? This popping force is really where you want to actually put in place to prevent the structure from actually swaying. Right now, so there will be a chance that if let's say you look into this particular structure, if you don't have this particular joint over here at C, right, what is going to happen to this structure? It's going to sway to the right, correct? Yeah, so very obvious. So the thing is that once you have this popping force, your structure will not going to actually kind of like sway to the left. So that's actually how you define the popping force and how you're going to calculate the forces. And this is how you actually calculate the popping force, right? So if you look at the solution, that means is that you need to find out what is the, okay, for example, in member AB and BC, right? You will be able to find out the reaction forces at actually, okay, for example, for member AB, you will be able to find the reaction force at B, which is actually pertaining to in the horizontal direction. Alright? So even in member BC, you will be able to find the forces in the, I guess for this case is B and C as well, right? Okay, anyway, so the thing is that if the what actually result in actually moving in this direction is that you need to find out all the horizontal forces along member BC, at point B and point C. So that would actually be the summation of all these forces will become the popping force. Alright, so with that, let's go and look into how the solution is actually they are all fixed ends, right? They're all fixed ends. So for this case, they're all fixed ends, right? Unless it's really like a cantilever beam, then it is actually like a free end. Right? So that's why you then have to actually apply the condition differently. Right? Okay, good. So I kind of like sorry. So if you come back to this particular structure, there are actually three members, right? Member AB, member BC, and member CD. Right. So for this case, if you look into because this particular force is actually kind of a lateral force, it's actually acting kind of horizontal, but this horizontal force is actually acting on the vertical member. So with that, for member AB, you'll be able to determine what is the force in, of course there's going to be a force in A and B, right? Based on the slope deflection method. Correct? That is the force. Or of course you're using moment distribution method, right? You are able to actually from the free body diagram draw the forces as well. Right? So the thing is that for this case you're going to have a horizontal force at B and at A. And after that, if you look into member CD, remember CD, right? You'll also be able to determine a force in a horizontal direction. Alright? So with that, you can then refer to the solution, right? Of course, in the solution, what it does is that you have to actually draw you need to actually do the moment distribution method, right? After that, then determine what are the moments over here. And after doing the moment, you then have to start to draw the free body diagram for member AB and member CD. Right? So with that, you will then be able to calculate what is the reaction forces acted in this manner. Right now, of course, what you are doing here is you need to realize for member AB, right? Where is actually member AB aligned originally? Because this structure is going to be this one, right? AB. So this is going to be fixed. This is A, this is B, this is C, and this is actually D. Alright, so what the solution does is that originally we are actually just considering this is going to be A and B. So this is going to be A and B, right? So what's the moment being, what's the moment that you determine at A and at B? If you refer to the notes, you'll be able to determine the moment. It is going to be, there's going to be a moment here, right? And there's going to be a moment here as well. If you are to complete the moment distribution method diagram. Correct? So where is AB? AB is actually, if you look into this table, right, this table, you obtain this is for member AB, right? For member AB, you will be able to get that the moment at node A along member AB is actually 134, right? And for at node B, within member AB is 31.5. Right now. So with that, that means what you are going to be able to do is for node A, what is the moment? The moment it will be actually 134. Yeah, correct. Why is it 134 and why is it in the anti-clockwise direction? Because the moment you gotten is actually minus. Correct? So this is actually 134 And from at node B, right, what do you get? You get actually 31.5. Correct now. So 31.5 is a positive value, and with that, you have to 31.4, and that is a clockwise movement. Correct? Because that's how you actually do. So after that, what the solution does is that it just actually flip over. Right? So if you want to look at from here, if this is the case, and what else you need to do, you need to actually consider there's also going to be a force of W that's actually acting at member AB. Right? So because this is going to be W, so if you were to actually draw the free body diagram for member AB, there's going to be reaction forces that is going to be kind of like experienced over here, where this is RA and this is going to be RB. Right now. So with that, you will be able to determine what is the reaction force at B, right, in the horizontal direction. If you do something similar for C and D as well, right, because this is going to be D and this is going to be point C, right? So for that, you would be able to actually, so for C and D, what are the moments acting as C and D? What is the moment at, okay, so what's the moment at C? The moment at C is going to be 11.4 and it's going to be clockwise or anti-clockwise? Clockwise, right? So this is going to be 11.4, right now. And your D? D is negative, right? No, it's actually 5.5. So it's 5.5, right? So that's why it's actually clockwise as well. So it's going to be in this direction, right? 5.5. And with that, you should be able to actually draw a reaction force at D and also a reaction force at C. Correct? So if you're able to do that, by right, you will be able to draw you should actually draw for BC as well. But if you were to draw BC, right, is there any horizontal force acting in BC? Actually, there's no horizontal force acting at BC. So actually, you don't need to consider this member BC. Alright, so with that, there's only going to be member as in AB and CD. You have to draw, and you have to calculate what is the forces at here, at RC and at RB. Right? So once you actually determine RB and RC, the summation of these two RA and RB will give you the popping force. Right? So you just have to understand what is this popping force for. It's really to prevent the structure from swaying. Right? So with that, you just have to find out what are the forces all acting along this particular distance, along this particular point here. Because you're going to determine the popping force at C, you see. So you need to find out all the forces that are actually acting in this direction, which is in the horizontal direction. When I focus on the solution, it actually kind of like flip, for the member, it kind of like flip to become horizontal because it's easier for us to actually work on that manner. Alright, so if let's say you are still not clear, we can then move on to, we can look into the next question. If you look at this question, right? This one. Correct. This is the third question, right? The tutorial question. So, how many kind of like reaction forces do you have to determine for this case? How many? So how many do you have to, how many so-called like free body diagram do you have to actually draw? 3. Why is that 3? Top 2. So basically it will be, you know, AD, right? You will be able to determine the reaction force at A in member A, AD. After that, in member BD, right? BE, you're also able to draw a reaction force over here. And at member CF, you're going to have another reaction force being drawn in here as well. So your purpose, your mission is really to, your task is really to find out what are all the reaction forces that are actually acting in the horizontal direction. So these horizontal direction forces will actually kind of add up to be the popping force where it has to be applied there to prevent the structure from actually swaying. Alright, so if you refer to the notes, I mean if you refer to the solution, that is actually how you are actually able to determine the popping force. Right? So is it because that you don't understand from the solution or you don't understand the steps at all? Is it? The force is acting on. Okay, you see, the thing is that for this question, you know that if the loading is actually being placed, of course, the popping force can actually be applied in different directions to prevent. So the popping force is really there to prevent the object from swaying in that particular direction. If this popping force is placed at C, and you know it's being placed there, you know that it's really going to prevent it from moving in the horizontal direction. So you just have to find out what are all the forces that are actually acting horizontally along this line, along this particular member. That is good enough. Alright? Okay, right? But if not, right, what if I give you another example? Right, so if you actually have I think in tutorial 1 or 2 we have actually quite a number of structures, right? Right, so what I'm going to do is I'm just going to give kind of like an arbitrary structure. Right, so this structure has how many members? How many members? Seven, right? Right, so for this case, I can ask you for how many popping force? Two, right? Because I can ask you for the popping force at E or actually at G. Alright? Well, of course, I'm not sure whether maybe I should actually put in another one here so that it makes better sense. Alright? Alright. So for this case now, in how do I determine the popping force at E? How do I determine the popping force at E? Okay, do you understand the concept? What I'm trying to say is that the popping force is really to prevent the structure from swaying, let's say, in terms of left and right. Right? So assuming that if there's a force acting in this W, but you know that the structure tendency is going to move or sway to the right. In order to prevent the structure from swaying to the right, you need to actually apply kind of like an opposite force, right, to prevent the structure from actually moving. So of course the popping force has to be applied at E and also at D to prevent this thing from actually kind of like moving. Right? So now if I'll ask about, okay, this one is a bit more complex. Let's say for at point E, right? How many reaction forces do I have to determine? How many? Two. Is it two? What else? Who else? Any? 2 or 4? How many? Why 4? We have 4. How many? Do I have any other numbers? 2 only, eh? So I can see now. Yeah, at E. 5. How many?
2.
Alright, if it's for E, how many?
2.
2. 4. So why is it 4? Right. So can you imagine it has to be 4, right? Why is that so? Because the thing is that you are able to actually draw. Okay, let me see. First thing, you can draw member AB, right? Right, AB. Okay, you can actually determine a reaction at B, right now. Of course, a reaction at A. So this is the first force that is moving in a horizontal direction right now. Of course, second, maybe you think is another why is it here? Because you're considering here where this is RE and this is RF, right now. So this is member EF. So that's 2. But where are the other 2 come from? Yeah, the top structure. Don't forget, you're still going to have your member BC. So BC, you need to determine what is the reaction force at B and reaction force at C also. Right now, and where is the fourth one? The fourth one will be at DE. Over here where this is D, this is E, right? You are able to calculate what is reaction at E and your reaction at B. Right now. So how many forces do you have to add up in this case? With 4, of course, RB with respect to, RB with respect to AB, right? Plus RB with respect to BC. And of course, RE with respect to EF and RE with respect to EE. So no matter what, how you want to give is that you have to understand what the stopping force is really to prevent the structure from actually swaying to the right? That's why you need to find out how many forces is there in the horizontal direction. That's how you actually determine the popping force. Right? And how about popping force at G now?
3.
3, right? Okay, I hope there's no other answer. It's 3. Why? Which are the 3? Of course, first thing is you get RC and you have RD. And what else? Next is that you're going to have, because this is going to be G and this is H, you'll be able to determine this is RG. This is RH. So for the popping force at G, you'll be a summation of this RC, RD plus RG. That gives you the popping force for G. Okay, so the question is how do you know the R is positive or negative? Yes? Anybody can answer?
Free body diagram.
Alright, so the thing is that I think as a start, we will always state our convention. When we write it right, we will always state that we always draw the arrow to be from right to left to be positive first. Right? After that, if you work out the free body diagram, you take rotation equilibrium and summation. Rotation equilibrium and translation equilibrium. If your force turns out to be minus 20, what does it mean? That means it's actually in the opposite direction. Right? So in terms of the convention, you want to actually stick to your convention where you might want to draw from right to left to be positive first. Of course, you assume that your working is all correct. And then your answer turns out to be negative, you know that the popping force is in the other side. Right? So, for example, if I know that this is going to be, maybe my RB is going to be 20 newtons, alright? And this is going to be minus 35 newtons, and RE is going to be plus 25 newtons, and RE is going to be actually minus 50. If you're based on this calculation, based on the arrow that you obtain, right? You obtain RB, this is 20 minus 35 plus 25 and minus 50. So what is the popping force at G? How many? Alright, any other answers? So what's the value? What's the popping force? But if you add everything together, right? Of course, you know, you will take the summation of forces in the x direction equals to 0. No, not 0, sorry. The summation of forces in the x direction is equals to, you have your 20 minus 35 plus 25 and minus 15, that will give you minus 40. Right? So that is actually the overall force in a way that the popping force is actually minus 40. Right? But how I interpret this is that because you look at the solution, it's trying to say that the total force is actually, okay, if it's minus 40, so what does it mean? Actually the whole system is actually going to the left.
Yeah.
Right now. So if you want to, I mean the whole structure is going to the left by right, the popping force has to be pulling in the positive direction. But I think what solution the Dr. York has is that you just have to, the summation of all these forces becomes the popping force. That is good enough. Got it? Right, so if you look into the tutorial solutions, that's how you actually determine the popping force. Sorry? Alright, so how do you get the popping force? Do you mean the popping force or individual force? Alright, so the question is that how do you get all the individual force? Are you able to get the individual force? How? How? If you want to start off with using, of course, if you use the slope diffraction method, you'll be able to get the PY1 and PY2, right now. But if you decide not to actually go with the slope diffraction method, how? If you decide to draw the table, the moment distribution method, and how do you do it then? Huh? Divide by distance. Okay, so the thing is that you need to then draw the free body diagram. That's what I actually showed it. So are you all clear with this really? So what is the concept of popping force is really whatever forces that are actually acting in the horizontal direction at a particular level. You have to sum it up. That is actually popping force, because if you don't sum it up, right, over here you know that maybe the total force is actually negative 40. That means it's actually moving from left to right? If you don't have a counter force, this structure is going to sway to the left. I mean, it's going to sway to the right. So that's the popping force you need to determine. Alright, so get this clear? Alright, so what we're going to do now is to let me just come back to, so let's look into question 3b. Alright, question 3b, let's come into this solution here. Alright. Alright, do you understand the working? How do you determine RA and RB? Right, basically it's actually talking about drawing that particular element, the free body diagram for that element. We will look into AB, right? By right, AB is what? Okay, sorry, come back to this structure. I think the AB is something like that, right? This is AB, right? By right, you need to actually draw the structure to be in this manner. So this is the kind of like the free body diagram that you have to actually draw for AB, right? And so for this is that how many forces, what are the forces they are actually acting in this particular member? So you need to find out if there any external force. For this case, for member AB, is there any external force? Yes, right, it's actually the W that is being applied. Correct now. And after that, what else? What else? Yes, there's going to be moments being induced at the two joints. So what are the moments? So the moments you have to actually refer back to what, remember what you have determined from the moment distribution method, the table. So if this is member AB and the moment is actually minus 134 and 31.5, right? So the moment at A is going to be minus 134. So the moment is going to be in the anti-clockwise direction, which is 134. And how about B? The B is going to be 31.5, right? 31.5 is positive, so that's why it's going to be in a clockwise direction, 31.5. Alright? And after that, so you put in the moments really, the next thing is that that's going to induce reaction force at A and reaction force at B. So with that, you actually complete the free body diagram for member AB. Right? And for this case, because the structure is in equilibrium, that means you can take rotational equilibrium and translational equilibrium. You can take summation moment about A so that the whole system moment is going to be 0. Right now?
我看的都是底下。
That's why if you refer to the solution, right? Right? What it says is that if you are to take summation of moment about, or you need the light to be. Right? So for this case, if you were to take summation of moment about A to 0, right? And for this case, if you consider moment in the clockwise direction as positive. So what are the moments they are actually acting? The moments acting, of course, will be this 31.5, right? And for this case, it's going to be 31.5, and of course, you need to factor in the W over W L over 800, right? This is the first moment. And what is 134? Because for this case, it's actually negative, minus 134 WL over 800. Right? And what else? What other forces is going to actually act at moment onto point at point A? The next thing will be W, right? And because W is going to induce a clockwise moment, so with that you have to be plus W multiplied by what is the moment arm? Because this length is L and this is L over 2. So that's why it's actually multiplied by L over 2. Right? And what else is the RB? RB is actually acting a anti-clockwise moment about A. That's why you need to minus RB and multiply by the distance, which is L. And all these things have to be equal to 0. Right now. So with that, will you be able to work it out? So you need to find what is RB. Because in a way, W and L are actually known kind of like values. Right, so with that, you will be able to determine your RB is equals to, right, it's equals to minus 102.5 W divided by 800 plus W over 2. Right? Alright, the question is how do I get 31.5 W over 800? Remember, it was actually from the moment distribution table. The moment distribution method from here, this is actually the moment, 31.5. But I think for this case, we will bring out another factor of W over 800. Fair enough? Yes, right. See, moment about A, when you take summation of moment, this moment is going to act at any point. So if you take moment about A, all these moments is going to contribute to the entire member. This is how you should take summation of moment. Because when there's a moment, you need to actually, this moment, no matter where you take, all these moments actually contribute to the summation of moment. Alright? Of course, the forces, you need to multiply specifically by the force with the distance with respect to O. But all the other moments is going to be included. Right. Why is that a special reason? Because I think if you refer back to the solution actually pull out WA over 800, WL over 800 so that you can actually work with a nicer number. If you refer back to the earlier working. Because if not, if you don't bring, for this case, can you see, right? If you don't, I think what the solution does is that it just can't working simply. If you take out WA over 100, right, your starting point will be actually minus 100. So it's a nice number if you start off with doing the moment distribution. No, No, not really. You really have to depend on what is the value that you're given. Because I think if you look at another example, right? Do you have other examples? Alright, you see, for this case is that maybe this is actually Dr. York's solution. He preferred to actually work on it using WAL over 800. If you don't want, right, you can work with the numbers as well. So 100, because the link said 100 divided by 800, what does it give you? 100, 1/8 is what? What is 1 divided by 8? It's 0.125, right? So instead of starting using 100, you're working with a number of 0.125. Do we want to do that? You know? Yeah, so that is actually his approach. Alright, can, right? So with that, by doing that, you will be able to actually solve for RB. That is actually for member AB for RB. And similarly, you need to actually solve the same thing for member CD as well. Correct? So for member CD, you have to, so your interest is to find out what is the RC. Because what it does is that the structure is, I think this is A, B, C, and D, right? Correct. So you need to find out what's the reference force at B and what's the reference force at C. So you will then be able to sum the two forces together. Right? Because that is the, again, this is the mobbing force at C. Right now. Good. So you really need to know how to draw the free body diagram and then take translation equilibrium. Once you take translation equilibrium, because for this case, what your interest is to find out reaction at RB, right? Of course, you don't need to take moment about B. Straight away you take moment about A, you're able to solve what is RB. Alright? And of course, I think you all have access to some exam papers also, right? So I think it's pretty common that you always wanted you to find out what are the moments at all the various members at various joints, and followed by determining the popping force. Right, so cannot run away, right? So you must know how to actually determine the popping force. Good. Alright, any other questions? Alright, drawing about the bending moment diagram. Okay, so which one do you want to actually, is there a specific example that you want me to use to illustrate? Okay, so I think popping force is fine, right? Any other questions about popping force? If not, then we move on to a different question. Okay, the next question is actually to draw bending moment diagrams. Are you all okay with drawing bending moment diagrams? Confused or? Alright, this one is from which year? 2015, is it? Is it included in the solution? No, right? Do they give you the solution? Alright, no, this one is by you or so you all get it from the seniors, is it? Yeah, alright. No, I don't need to redo lah. Maybe let me see whether if I have the working enough for 2015, right? there's another question. This one is actually from 2015.
Good, the mic is working. Oh, mic.
Right, so have anybody attempted this question? 2015? I guess, I heard you all have the solution, right? You don't have it? Some of you have the solution. Alright, so let's try to, do you want me to go through from the beginning or you just want me to go straight? Alright, so what I'm going to do is that this is the question that's actually given, right? So what it does is that it's first asking you to determine, okay, there are three questions needed, right? So determine the bending moments at the nodes A and D, right now. So at nodes A and D, and of course then the popping force at C, and last but not least, draw the bending moment diagram for the frame, right? Let me just go through briefly. So you can see that this is the structure, right? A, B, C, D. Which member is being loaded? It's only BC that's being loaded, right? So for that case, you will then have to actually find out what is, because you know that this is going to be uniformly distributed, right? This is B and this is C. So with that, you need to actually go and determine what is the fixed end moment that's being induced, so that you're going to put it into your moment distribution method table, right? So for this case, you will be able to determine what is these two moments using the formula that you need to memorize, alright? So after that, eventually what I'm going to do is, let me just try to work out the final table. If I'm able to, this is A, B, Alright, so of course you need to work out the moment distribution method table yourself. Eventually, what is the moment that I'm getting? The moment over here, I'm actually putting in terms of kilonewton meter. Alright, so the moment at A is 0.1844. Alright, and the one at B, which is A, is 0.3705. And BC is minus 0.3705. And C is 0.4101 minus 0.4101, and last but not least is minus 0.2041. Okay, assuming that you need to arrive to this final row of the moment at each individual, and of course the question is asking more specifically for at nodes AD. Right, so we are looking at the moment at A and at D. Of course, we can ask you for any other joints as well, or any other nodes. Right, so for this question, make sure that A and D are obtained. Right, so next thing now is to determine the popping force at C. Right, so if it's for popping force at C, what are the members you need to consider? What are the members you need to consider to determine the reaction forces? AB. Alright, what else?
CD.
AB and CD, right? Because AB and CD is you are going to actually induce horizontal forces. Alright? So with that, let's start off with AB. We need to determine the shear force at AB, which is draw the figure diagram. So for this case, if it's in AB, right, let me just try to draw the A and B. Right, so I just take the member to be vertical, so that I know which is the force that I need to actually take. So how do I complete this free body diagram? As I said already, of course you draw the physical member of AB, then you put in the moment first. Right, so what are the moments that's being generated in this case? So you know that it's actually A and B is actually within AB. So let's start with A. What is the moment generated at A?
0.1844.
Where do I get a number? Because it's here, right now. This table, and it's actually positive value, you know that it's going to be in clockwise direction 0.1844. 1.44. Right, this is kilonewton meter. And how about B? B is equal to what? What is the moment at B?
0.
Okay, 0.3705, but which direction is it going to be? Why is it clockwise?
Positive side.
Because it's positive, because I'm taking this value. Right, so with that, you know that it's also going to be clockwise, and this is going to be 0.3705, like kilonewton meter. Right, after that, you then have to draw what is your RA and what is your reaction at RB. So these are the two by right, the RA and RB that you need to determine. For this case, because member AB do not have any external forces. Right, so this is the complete free body diagram. And now your interest is to determine RB, right? Because RB is where it's along it's actually horizontal to the popping force at C. Right, so you want to do, for that case, you want to take summation of moment about A equals to 0. Right? So with that, by doing that, you define your clockwise as positive. You will get 0.1844 plus 0.3705, right? And for RB, is it positive or negative? It has to be negative because you're going to minus. What is the height? No, the length is 1.25, right? So it's 1.25 multiplied by RB equals to 0. So by doing that,